that white screen. Okay, so I can start. So you are already familiar with this, that is that compact topological space. You are already familiar with that. Maybe something will be repeated for you. So here I start. So compact topological space. So here is the definition. You already know the definition. So a topological space X is said to be compact if every open covering this of X has a finite subcollection we can write which covers X, or we can write only covering X. Okay, so that's mean, what does it mean? So that's mean if we take, say, so first of all, you may ask, so what is the open covering of A? What is the open covering A of X? So that's mean open covering A of X. So what does it mean? So that's mean A is a collection of open sets, say U alpha, alpha belongs to some index set lambda. So open sets of X. Okay, so A is a collection of open set of X such that if we take all the union, that will be X, where this is this collection. Okay, right? And X is said to be compact if we choose any such open covering of X, then it has a finite subcollection such that, so there exists U1, U2 up to UN. We can write this such that UI belongs to this and union of I equal to 1 to N, UI equal to X. So this is the meaning of X is compact. That's mean if we choose any open covering of X, then it has a finite subcollection covering X. Right? You know the definition. So here is one example. So first of all, if we take X equal to, say, by open interval, this one. Now is this compact? Yes or no? Why you are taking that much time? If you don't know
No,
the
sir.
then you should say it is yes or no. Not compact, right? Not compact, right?
Yes, sir, it is
Yes, sir.
compact.
It is compact? Yes or no? Someone saying that it is compact.
Sir, we can take two open intervals, 0, 1 and 1 and 2.
So you are saying that this is compact.
No.
So what is the definition of compact? So if you take any open covering, so can you give, it is not compact. So can you give one open covering which does not have any sub collection covering X? Hmm?
0 plus 1 by n comma 1.
Right, just you can take an equal to 1 by n comma 1. This one. Now then if you take this collection, n belongs to natural number, then if you take union natural number an, then that will be X. Right? But it does not have any finite subcollection. So this collection does not have any finite subcollection covering X. Or you can say that which covers X. Covers X. Okay, so this is not compact. Now what about, now you have to be hurry. Okay, so you should not take that much time to think of this simple problem. Now what about if we take X equal to that set 1 by n, this one. What about this? Is this compact or not? In that
No, sir.
usual
No, sir.
topology.
No, sir.
No, again the similar region, right? Now what about union 0? Is this compact?
Yes, sir.
Yes. Why?
So, like if I take any open cover containing X, then I know that 0 belongs to that open cover,
Right.
so
Then that will contain,
that contains
right,
infinite nodes.
all the elements except finitely many, right, is compact. So this was not compact, but this is compact because any open set containing 0 must contain all elements of X except finitely many. Right? So now this is clear. Now there will be lots of examples of compact or non-compact. You can just go through that examples and go through the exercise from the Mooncrest. You will get fine, and you have also already seen that. Now the question is how to show a subspace is compact. Suppose Y is a subspace of X. Okay, so this is subspace. So Y is a subspace of X. And we want to say that Y is compact. Compact or not, we need to check, right? So suppose we need to check that Y is compact or not. So that's mean what we will take? We will take a open covering of Y. Now the question is how shall we take the open covering of Y? That's mean from where we take the open sets. Shall we take open sets from Y or open sets from X? Tell me. Did you get my question? So Y is a subspace of X and we want to show that Y is compact or not. We need to check that. Then from where we will take the open sets from Y or from X.
Why?
Right. Actually, the definition says that you can see the definition. It says that a topological space X said to be compact if every open covering has a finite subcovering. And what is open covering? Open covering means open sets of X. That's right. So that's when if we want to check that Y is a compact, then from the definition it is clear that we need to take the open sets from Y. That is the definition. Right? Now we will state a theorem now. It says that it does not matter. You will take open sets from Y or open sets from X. That does not matter. Okay, so you can take open sets from X also. Okay, and in that case, you will have here that one will be a superset of Y. That's all here. Okay, now I state the theorem. This is very simple proof, but you should know that. So this is a conceptual one. Now Y is compact if and only if, okay, for every open covering of Y consisting open sets in X. Okay. So for every open covering of Y consisting open sets in X, that's mean that open covering, say this one, okay, and it has the open sets from X itself. Has a finite sub collection which covers Y. So that's mean here A is U alpha, where alpha belongs to these sets, where U alpha is open in X and union of this, that is, or you can say that it covers Y. Okay, and we say that it has a finite sub collection which also covers Y. Is the statement clear? So that's meant to show that a subspace is compact or not, it does not matter from where you take the open sets. You can take the open sets from X itself, or you can take the open sets from the subspace. Is that clear, the statement? Yes or no?
सर फिर से रिपीट
Yes,
करना
sir.
एक बार.
सपोज मान लो कि X एक टोपोलॉजिकल स्पेस है, ठीक है, एंड Y उसका एक सबसेट सबस्पेस है, तो तुम्हें ये दिखाना है कि Y कॉम्पैक्ट है कि नहीं. तो इसलिए अगर तुम जब दिखाना चाहोगे कि Y कॉम्पैक्ट है कि नहीं, तो तुम्हें एक ओपन कवरिंग चूज करना है. अभी ओपन कवरिंग में क्या होगा कि ओपन सेट चाहिए. नाउ द क्वेश्चन इज कहां से तुम वो ओपन सेट्स लाओगे. नाउ ए थ्योरम बोल रहा है कि तुम ओपन सेट्स X से भी ले सकते हो और Y से भी ले सकते हो, कोई मैटर नहीं करेगा. ठीक है.
ओके सर.
So first of all, assume Y is compact. ओके, तो इसको मैंने कॉम्पैक्ट मान के चल रहा हूँ. ओके, Now let this U alpha is open in X and Y subset of union of this. Okay, that's mean A is a, the script A is a open covering of Y consisting open sets in X. Okay, so that is this is a open covering of Y consisting open sets in X. Okay, so now let V alpha equal to U alpha intersection Y. Okay, then तुम इसका नाम दे दो A dash. Now that is the collection of V alpha. This. Okay, now where V alpha is open in where Y and Y equal to union of V alpha, right? So that imply A dash is an open covering of Y consisting open sets in Y. Now since Y is compact, so A dash has a finite subcollection covering Y. So that is, so there exists V1, V2, Vn belongs to this such that Y equal to that union of Vn. Now where Vi equal to Ui intersection Y. Now that imply you can write union of Y equal to 1 to n Uy, that is superset of Y, and Uy belongs to A. So that is this has a finite subcollection covering Y. So we are done. Is that clear? So that's mean if you want to say that Y is compact or not, you can choose open sets from X itself or you can choose open sets from Y itself. So that does not matter. Is the proof is fine to everyone? या फिर समझ में
Yes,
ही नहीं
sir.
आया कि क्या हो रहा है? अभी इसका कॉन्वर्स प्रूव करना है कि कर पाओगे?
कर लेंगे सर।
कॉन्वर्स सिंपल है अभी, मतलब सिमिलर ही है। तो अभी कॉन्वर्स में क्या करना है, सपोज ए प्रॉपर्टी होल्ड हो रहा है और तुम्हें दिखाना है कि y इज कॉम्पैक्ट, ठीक है? तो हम क्या करेंगे, हम पहले अभी एक a डैश ले लेंगे v अल्फा। देखो मैं बता ही रहा हूँ कि सिंपल ही है। अब क्या करेंगे, a डैश ले लेंगे V अल्फा होगा ओपन इन Y सच दैट दिस, हमें दिखाना है कि A डैश के एक ओपन फाइनाइट सब कवरिंग रहेगा। ठीक है, मतलब फाइनाइट सब कवर, फाइनाइट सब कलेक्शन रहेगा कवरिंग Y, हमें ये दिखाना है। तो हम सिंस V अल्फा इज ओपन इन Y, सो हम V अल्फा को लिख सकते हैं कैसे, ऐसे U अल्फा इंटरसेक्शन Y where U अल्फा इज ओपन इन X, सो देयरफॉर हमें एक A डैश से A डैश से A मिल जाएगा जो एक ओपन कवरिंग ऑफ Y है एंड consisting open sets in X. Now by the given condition we have a finite subcover and then again जो U1 U2 मिलेगा हम उससे देयर एग्जिस्ट V1 V2 Vn भी मिल जाएगा, सिंपल है। ठीक है, ओके। तो इसके मतलब अभी हमें ये पता चला कि कोई भी अगर सबस्पेस को हमें कॉम्पैक्ट दिखाना है तो हम ओपन सेट्स जो बिगर स्पेस है वहां से भी ले सकते हैं। तो अभी जनरली हम वही करते हैं कि कोई भी सबस्पेस को अगर ओपन कॉम्पैक्ट दिखाना है तो हम उस सबस्पेस से नहीं लेते हैं, जनरली हम क्या करते हैं कि जो बिगर स्पेस है वहां से जनरली ओपन सेट्स ले लेते हैं। तो प्रूफ ज्यादा सिंपल रह होता है। ठीक है, नाउ हम ये प्रूफ करेंगे। You know that. Now let X be a topological space. ठीक है, now let C be a closed subset of Y X. Now then C is also compact. हमें A दिखाना है कि मान लो कि X अगर एक टोपोलॉजिकल स्पेस है, सॉरी कॉम्पैक्ट टोपोलॉजिकल स्पेस। ओके, तो अगर X कॉम्पैक्ट है, ठीक है, एंड C इज ए क्लोज्ड सबसेट ऑफ X है, देन C इज ऑल्सो कॉम्पैक्ट। ठीक है, नाउ इसका प्रूफ तो तुम लोग देख भी चुके हो आई थिंक रियल एनालिसिस कोर्स में। सो कैन यू गिव सम आइडिया हाउ टू प्रूव दैट? So we need to prove that C is compact and given that X is a compact topological space. So how to prove it? Now give me the approach. So first of all, what we'll take?
We can take an open cover of C.
Right. So let this be an open covering of C. तो हम ओपन सेट्स कहां से लेंगे? ए के ओपन सेट सी से लेंगे कि एक्स से लेंगे? That does not
It's
matter.
better to take an X.
हाँ, so बेटर है बता देना कि कहां से ले रहे हैं। हाँ, ओपन सेट्स इन एक्स, क्योंकि हम जब ओपन कवरिंग बोल रहे हैं कि तब वो क्लियर नहीं है कि ओपन सेट्स हम सी से ले रहे हैं कि एक्स से ले रहे हैं। सो बेटर है कि बता देना कि कहां से ले रहे हैं। तो कंसिस्टिंग ओपन सेट्स इन एक्स ले लिए, ओके, एंड देन
Then I know C is closed, so X minus C is open.
right. Now then if we take this collection, this union X minus C is a open covering of X, right? Why? So since C is closed, so X minus C is open in X, right? तो हमें एक open covering मिल गया। Now given that X is compact, Now since X is compact, okay, now there exists a finite subcollection of A dash which covers X, right? Finite subcollection, we can name it is say beta dash. Okay. Now let B equal to beta dash set minus this one. तो इसको हम हटा रहे हैं, ठीक है। तो ऐसा हो ही सकता है कि बीटा डैश में ए एलिमेंट नहीं है, तब भी ठीक है, क्योंकि हम सेट माइनस ऑलवेज कर सकते हैं, है ना। सो वी कैन डू ऑलवेज सेट माइनस। ओके, नाउ सिंस C intersection that X minus C is empty, so therefore B that beta covers C. Right? Now this is obviously, we can say that this is subset of this A and beta has finite element. Okay. So thus this has a finite subcollection covering C. So that is C is compact. So we are done. Now just quickly go through the proof. Now ask me if you have any doubt or if you feel something is wrong or anything like that. If you have any comments, just let me know. Fine, it is. जल्दी कमेंट बताओ, कोई कमेंट है? क्या हुआ? कमेंट इधर होगा या फिर नहीं होगा, दोनों तो नहीं होगा ना। यस और नो? सुना नहीं क्या? कितने लोग क्लास कर रहे हो कि कोई बात ही नहीं कर रहा है?
No, sir, we don't have any comment.
Okay, then you should tell that na. You should say loudly. I don't know. So you are had 23 people, but I don't know actually. So you people are listening or not? So if you are listening, then you should unmute and speak. That is the simple way.
Okay, sir.
Okay. Now tell me what about its converse? So that's mean Suppose X is a compact topological space. Okay. And C is a compact subspace of X. Can we say that then C is closed? हमें ए पता है कि X अगर compact topological space है and C एक closed subset है then C must be compact. हमें ये पता है ना. मान लो कि अभी थोड़ा सा इसका कॉन्वर्स लेके चल रहा हूँ कि X compact topological space है, ठीक है, और C क्या है, एक closed एक compact है. C एक compact subspace है. देन क्या हम बोल सकते हैं कि C closed भी होगा?
No, sir, it need not be true.
Okay, so do you have any quick counter example for that?
Sir, we can take x to be a finite set. Like if we take x is equal to ABC, and we can then define some topology. Like we can define the topology tau with the phi, singleton A, singleton B, AB, and X. Then AB, matlab set A comma B is compact, but it is not closed.
हाँ, अच्छा, हाँ, एक क्विक एग्जांपल दे दिए. Good. Because when I was thinking, I always assumed that cofinite topology. But that simple argument will also work. Because if you take cofinite topology, then actually you can take any subspace of that will be compact. Because if you take one open set, its complement has only finitely many. So any subspace, including that, if you take R with cofinite topology, if you take any subspace, in fact, if you take R itself, then also it is compact. But you can find many open sets which is many sets which is not closed. For an example, you can take set of rational number in R, right? So that is neither open nor closed, but that is compact in the cofinite topology. Okay. Now when you can say that a compact subset is also closed, when you can say that. So now we will see one theorem. So when we say that theorem, so that's when here we have seen that in a compact topological space, okay, compact is not needed here, okay. Now that Hausdorff will work actually. So let X be a Hausdorff topological space. I think we do not need compactness of X. Now let Y be a compact subspace of X. Okay. Now then Y is closed in X. ओके तो हमें x का कॉम्पैक्टनेस नहीं चाहिए, बट x को हाउस्डॉफ होना चाहिए, ठीक है. नाउ अगर x हाउस्डॉफ है एंड y इज इफ y ए कॉम्पैक्ट सबस्पेस ऑफ x है, देन x मस्ट बी क्लोज्ड. So the situation is like, so this is my x. Now say this is my y. Okay, so x Hausdorff, y compact. Now we show that y is closed in x. Okay, so we claim that, we actually proved that. We proved that. So x minus y is open. Okay, so how to prove that x minus y is open? So we choose a point here, say x. Okay, say take any arbitrary point. Now let x belongs to x minus y, and we found one open set containing this, which is lies in x minus y. So that's mean any point in x minus y is an interior point. So we are done. Now we need to find one open set U in X such that X belongs to U subset of X minus Y. Right? So therefore, now this will imply X minus Y is open, that is Y is closed. Is that fine? Right? हमें बस क्या दिखाना है कि x एक पॉइंट ले लेता हूं जो y से बाहर है, दैट्स मीन x माइनस y से है, देन हम दिखा देंगे कि वो पॉइंट एक इंटीरियर पॉइंट भी होगा. So that's mean we have a open set, that is open neighborhood, right, which totally contained in x minus y. Right? That is simple. Now how to find these open sets? Okay, now is this clear up to this portion? Yes, is that clear?
Yes, sir.
Okay, so how to find these open sets? Now take any y from y. Okay, now then obviously x not equal to y, right? Because y is in y and x not in y, so therefore they are not equal for any y, right? Now given that x is Hausdorff, now since x is Hausdorff, so there exist open sets Vy and Ux such that x belongs to Ux, y belongs to Vy, and Ux intersection Vy. Okay, we will take both notation y. That is empty. So that's mean this is my y. So we take one open sets here, and we can take another open sets in this way. So this blue one is my u y, and this is my v y. Okay, we always have that. For see now this open sets uy and vy depends on the point y only, right? Not in x. Okay. Now then if we take this collection Vy, y belongs to this covers y, but it is given that since y is compact, so there exists u Vy1, Vy2 up to Vyn such that V the union I equal to 1 to n this yi that is contains y. Is that fine? कोई डाउट है तो बताओ. Yes.
No, sir.
ये जो ऑनलाइन क्लास है ना, ऑनलाइन क्लास में स्टूडेंट्स का सब कुछ चला गया है, किसी का कोई कंसंट्रेशन है नहीं. सब लोग बस हाँ रिकॉर्डिंग है, रिकॉर्डिंग से देख लेंगे बाद में. Okay. Now can you tell me that how to find this y? U, this u, how to find this u? Any idea?
So we will take the intersection of u by I for I from 1 to n.
Right. Now we let u equal to uy1 intersection uy2 uyn. Take this. Now since x belongs to uyi for all I, that means x belongs to u and u is open. Why? Because it is only just a finite intersection of open sets. Okay, this. Now, right. Now U intersection this. Now that is empty. Why that is empty? We can write here claim. So let Z belongs to U intersection this. Now that imply Z belongs to this. That imply Z belongs to say Vij for some j belongs to this number n. Now since this, so now that imply z, since z belongs to vij, so this does not belongs to uyj, as Hello, can you see?
Yes, sir.
Yes,
So I got disconnected. I don't know. So okay. So up to which part was done? I got disconnected in between. It is recorded. Okay, fine. Yes. Now up to which part I have done? I have done up to this, or do you remember?
So second last.
Okay. So second, I was in here only.
Yes, sir.
Oh, okay. So see, if there is a Z between in this intersection, so that's mean Z belongs to this union, right? Now Z belongs to union of this. So therefore, Z should be in Yj for some J, right? Now we know that this one, that is Uyj and Vyj, their intersection is empty. Now if Z belongs to Vyj, then Z does not belongs to Uyj. That is simple. Now since Y subset of Uyj, right, because it is the intersection, so therefore Z does not belongs to U as well, right? Now this is a contradiction. So this is a contradiction. We can write if possible, right? So therefore this is empty. So therefore U intersection this one, now that is empty. Now again V, not V, that is Y subset of this, right? So that imply U intersection Y, that is also empty. Now that imply U subset of X minus Y. So we are done. So we are done. Okay. So therefore Y is closed. Okay. Fine. Is this part is clear to everyone?
Yes, sir. Clear.
Okay, fine. Hmm. Right. Now there is another interesting theorem. It says that continuous image, that is, you can say that continuous image means that image under the continuous function of a compact set is also compact. That is also simple. So let f x to y be a continuous function. Continuous map, and let x be connected. No, not connected, compact. Compact topological space. Okay, now then fx is compact. Now the proof is very simple again. So let this be a open covering of f of x, right? Now let say a dash equal to, now f inverse u alpha or u, where u belongs to this. Now then this one is an open covering of x, right? It is clear since u is open in A and f is continuous, so this is also open, right? And since A is a cover of fx, and if we are taking that inverse image of those maps, so they are in those sets, so therefore this is also covers x, and also elements of A dash are open. So this is an open covering of x. Now since x is compact, now there exists f inverse u1, f inverse u2 up to f inverse un belongs to A dash, which covers x. Now that imply u1 un covers fx, where ui belongs to this. So thus f of x is compact. Here we can give that region. So since u is open in y, so f inverse u is open in x. Fine, that is very simple. Okay, so I hope this is clear to everyone. Now there is another one that is very interesting. Now I expect that you will give the answer of this question. Theorem. Now let f x to y be a continuous surjective function. Okay, and x is compact. We can write given x is compact and y is Hausdorff. Now then f is a homeomorphism. Now, can you give the answer of this question? F is a continuous surjective function, X is compact, Y is Hausdorff, then F is a homeomorphism. Give the answer of this. That is not a difficult one. Yes. If people are listening or not, yes or no. If you are listening, then you should give the answer. That is not a difficult one. So what we need to show for to show that it is compact or not? Okay, so what about just what? Are you listening?
Yes, sir.
Hmm. How to show that a map is homeomorphism or not?
Sir, F and F inverse are continuous. Then F is homeomorphism. F
Right. So
inverse.
how? Right. Now how to go approach this one? Then what we need to show? It is given that it is continuous. It is given that it is okay, not surjective, bijective. Okay, it is given it is continuous. It is bijective as well. We just need to show that F inverse is continuous. Or we can show that F is a open map or closed map. Then also we are done. Since it is a bijective function, so open map imply actually F inverse is continuous, right?
Sir, if we take a closed subset C of X, then it will be compact because X is compact.
Right.
Therefore, f of C, its image will be closed and its image will be compact. F of C will be compact and f of C is the subset of Y, which is Hausdorff. So f of C will be closed in Y.
Right. That is very interesting and very simple one, right? Now first take, so let C be a closed set in X. Now that implies C is compact. Why? As X is compact. Now that implies F of C is compact. Why? As F is continuous. Now that implies F of C is closed. Why? As Y is Hausdorff. So that implies F is a closed map. So thus F is homeomorphism. So we are done. Okay? Because otherwise it is given. F is continuous given, F is bijective is given. Right. So now these are all about this compact, the theorem of compactness, and now I need to one big theorem. So that was very simple. Okay, now that is you have to be very you have to give very concentration here. Okay, So because that is not an easy one, but interesting, but not an easy one. Now it says that if X and Y are compact, then X cross Y is also compact. Now once you prove this, you can also prove that by step that a finite Cartesian product of compact spaces are also compact, right? Because you can take x1 cross x2 cross up to xn. Now since x1 and x2 is compact, so x1 cross x2 is compact, then product with another one, then that is compact, product with another one, that is compact. So up to finite number of states you can do that, right? So therefore product of finite number of compact spaces is also compact, right? You can prove that. Now how to prove this one? So X is compact, Y is compact implies X cross Y is compact. Okay. Now note that now for each X, so X cross Y is compact. Why that is compact?
Because it is homomorphic to Y.
Right. So here we getting that being homeomorphic to Y. Right. Now we will prove this directly. Okay. So now let this be an open cover of this X cross Y. Okay. And what we need to find a finite subcover of A. Okay. Now we take this. Now since this is compact and this A covers this one X cross Y, obviously that A also covers this. Is that clear? Is that clear that A, that script A covers this line X cross Y? Is that clear?
Yes, sir.
This is trivial, right? Now since this covers this, so there exists a finite subcover, so sub collection. So A1, A2, AN subset of this such that X cross Y subset of this. Fine. Okay. Now let we need boxes. How to find boxes from this? No, we cannot find boxes from here. Okay. So we cannot do this first. We can do this, but it will not help us. Okay. We will not take a finite subcover now. Now this is open cover. Now for each x, oh, that is compact, that is also fine. We have taken that. Now for each y, okay, there exists an element ay such that x cross y belongs to a y. Okay, right. Now there exists a basis element, so u y cross v y such that x cross y belongs to u y cross v y belongs to a y. Now is that fine? So what we will take? We will take that first of all. So we have that x cross y. We are taking that line, this one. Now for each element, we first choose a basis element such that that basis element subset of this. Okay. Now then, now this collection u y cross v y, y belongs to y, covers x cross y. Is that clear? This covers this line. Yes or no? Yes.
Yes, sir.
Okay. Now since that x cross y is compact, so there exists say u1 cross v1 up to u n cross vn such that their union I equal to 1 to n ui cross vi, that is, that covers this, and ui cross vi subset of some ai, and that is belongs to this. Now is that fine? Now what we get actually, now this is my x cross y. We are taking this line, so that is x cross y, this line, okay, and we are, this is by some boxes in this way. So we have some, we just covers this by some finite boxes. Now this line is x cross y. Is that clear?
Yes, sir.
Fine. Now what we'll do? Now from this, what you can say that now this boxes covers x cross y. Now from this, what you can say regarding that vi? Can you say that union of I equal to 1 to n vi covers y? Can you say that?
Yes, sir.
Yes, because of this is just a strip, right? Now then, union of I equal to 1 to n vi, because of that box, we have that flexibility that covers y. Okay, now let Wx equal to U1 intersection U2 up to Un. Okay, now then now x cross y. Okay, now that is subset of Wx cross y. Now that is subset of union of I equal to 1 to n ui cross vi. That is subset of union I equal to 1 to n ai, where ai belongs to that script A. Now, is that clear? Now tell me if any of the inequality is not clear to you. Any of the not inequality, any of the subsets. So we had
Sir,
this subset of this, we just find in between a tube. So that's when we have this only finite number of this. Now we just find one tube between this.
So it will be intersection then.
Which
Wx will be intersection of ui's.
inter sorry. Hmm. Okay. Now this portion is clear, obviously. Now what about this one? Now this is also clear. You can take one element from this, you can find from elements there only. Right? Because if you take one element, if you take say some z cross w belongs to now wx cross y. Now that imply z belongs to wx and some w belongs to y. Now since this is belongs to y, so that imply w belongs to some vj for some j, and from this z belongs to ui for all I. Now that imply z belongs to uj cross vj. Right? So therefore this is subset of this union. Okay? This. So from this, or actually we can say that thus for each x we have a tube wx cross y which covers by finite elements of this. Okay, so for each x we get a tube this which covers by finite elements of this. Okay, now we take this all tubes, only this one. Now this covers x. Now since x is compact, so there exists finite subcollection wx1, wx2, up to wxm such that x subset of wx1 union wx2 union up to wxm. Now that imply x cross y subset of wx1 cross y union wx2 cross y wxm cross y. Okay, now since each of wxi cross y is covered by finite elements of A, so therefore x cross y is covered by finite elements of A itself. So thus x cross y is compact. That is very simple actually, just conceptual. So what we did actually, so we have this total x cross y. Now we choose for each x this, we choose this line. Now this line is x cross y, right? Now we find a tube containing this tube. Now this covers by finite elements of A. Now what we do? Now we have this one. Now since x is compact, now this open interval is actually wx, and this tube is wx cross y. Okay. Now what we do? Now this one. Now we, since x is compact, now that is union of this kind of uh, tube, finite tube, right? And each of this tube, now each of this tube covers by finite elements of A. So therefore whole x cross y covers by the finite elements of A. Now tell me, so if you have any doubt on this. Fine. Yes, yes. If you have any doubt of this one, now you can also ask. And if you don't have, if you feel that it is fine, you understood the concept, then you can say so that I can proceed.
Fine, sir.
Okay. Right. Now I close this lecture with one remark. Remark means there is one actually theorem which is called that, I think you have you know this one, that finite insertion property. FIP, that is finite intersection property. Now what is this property? Now a collection, say beta of subsets of X has finite intersection property if for any finite subcollection say B1, B2 up to Bn subset of beta, we have this intersection is non-empty. Okay, now this is called finite intersection property. That's mean if you choose any finite subcollection, then that is non-empty. If you take any finite, okay, you remember that any finite subcollection of this, then it is non-empty. Now there is a theorem which is actually straightforward. Now theorem is X is compact if and only if for any collection of closed sets, collection say beta, sets of X having that finite intersection property, in short we can write FIP, okay, having finite intersection property, the intersection this that is non-empty. That is the theorem. Now X is compact if and only if any collection of closed sets having finite intersection property, that is having this property, has this intersection is empty. This is if and only if condition. That is very straightforward theorem. Okay, so I am not going to prove this because you have to feel this one. That is very simple. For an example, now how it is simple, you can check that. See, we assume that X is compact. Okay, and also now we assume that X is compact and we need to prove that these statements. So we take a collection beta of closed sets having finite intersection property. Okay, now we claim that this is empty. Now we prove this by the contradiction. Now suppose this is not empty. Now if this is, sorry, we have to prove that this is not empty, right? Now suppose this is empty. Suppose this intersection is empty. So therefore, if you take complement of B complement, if you take B complement and union of B complement, that is will be whole X, right? Suppose this is empty, equal to empty. Now take complement on both sides. Now that empty sets complement is X and this complement will be union of B complement. Now B is closed, therefore B complement is open. So therefore the collection B complement is a covering of X, right? Now since X is compact, so it has a finite subcover, right? So there will be some B1, B2, Bn such that union of Bi complement equal to X. So therefore this intersection is empty, and which is a contradiction that it has finite intersection property. So this part is not true, right? So therefore X is compact will imply this. Okay. Now similarly, suppose this property is given and you need to prove that X is compact. Now again, since you need to prove that X is compact, take a open covering of X, say U alpha. U alpha, right? Say A is an open covering of X, right? Now, since it is an open covering of X, so that is very simple actually. Now take this open covering of X. Now this is say A alpha, alpha belongs to this. Now that's mean X equal to union A alpha. Now that imply MT equal to intersection A alpha complement. So therefore, this, since this is empty, so therefore this collection does not have that finite intersection property, right? Because if this sets, this collection would have finite intersection property, therefore this should be non-empty. But since this is empty, so therefore it does not have finite intersection property. And that imply, so there exists alpha 1 up to alpha n such that intersection of I equal to 1 to n A alpha I complement equal to empty. So therefore X equal to union of A alpha I. So therefore this is a subcover of X, finite subcover. So X is compact, right? So this is very straightforward one. Now just try this. That is very simple. I hope you can prove this. Is it fine, right? I think you have you seen that this theorem before in your calculus course? Yes or no? Have you seen this? No, but this is simple, right? You can just connect this one. Just try to find, try to prove this. Though I have proved here, just try to write this. So if you cannot prove this kind of theorem by your own, that's mean you did not learn anything from the topology course. You should write this kind of theorem by yourself and without taking help from books. You have to do by yourself. So if you can't do this, that's mean you have not learned the topology course. Remember that. Okay. Just complete the proof. Also, do not see what I have told now. Even don't go through the lecture videos also, because I have already told that converse part and this part I have proved here. Okay, don't go through that. Just take the theorem and prove by yourself. Though proof is given in the Munker's book, but don't see that. Just prove by yourself. You have to prove this kind of easy theorem by yourself. Okay. Okay, fine. So we can stop as
Theorem,
well. Huh, Balo?
what about the converse of that?
Yeah, that is if and only if. Converse